Okay, welcome back, everybody. I hope everybody is well and healthy. Are there any questions about the Hamiltonian material so far? I'm just going to quickly review what we did last time anyway. Okay. So this is what we did last time. We got started with Hamiltonian systems, and I think not only last time, but the time before, I started giving you examples of various Hamiltonian systems to give you an idea that this is an important class of systems to look at because it arises in various areas of applied science that on the surface even have not much to do with each other. And once you establish that the system is Hamiltonian, you will get a lot of properties for free so that you don't have to do the analysis on the system, or qualitatively, you immediately know what to expect when you study the system. So that means somebody gives you a numerical result, you already have a printout, a picture, sends you a picture, you already have certain expectations. And if they are not met, then it's for sure that there's something wrong with that code, or you just didn't remember the properties of Hamiltonian systems correctly. That's always an option. That's why you have to learn them well. So what's a Hamiltonian system? I'm not going to redo everything. I just need the definition. Is the Hamiltonian system is always an even dimensional system whose variable x in the phase space can be partitioned into two groups. You have essentially position type variables, even though this is not, it doesn't have to be position. It's just that the mechanical intuition that tells us that one set is like position and the other one would be momenta, or sometimes called canonically conjugate momenta. These sometimes are called canonically conjugate variables, referring to the interesting skew-symmetric relationship that they have through a given function h that can be dependent on q, p, and t. Function has to be differentiable. It's called the Hamiltonian. And a shorthand notation we've developed is that if you just want to write one variable x for that contains both q and p, you can do so, right? It's a much easier notation to work with. You just have to introduce this, what's called the canonical symplectic matrix. It's a skew-symmetric matrix with n by n identity here and minus identity there. And if you apply that to the gradient of the Hamiltonian, that it tells you that a Hamiltonian system is not quite a gradient system. It doesn't derive as a gradient of a potential, but in some sense, it's a generalized gradient system or a skew gradient system, because you have this skew-symmetric matrix that repartitions, redistributes the derivatives. The upshot is that still the promise of the Hamiltonian formulation is just by studying the scalar valued function, because the scalar valued function, you can understand the properties of the system and do analysis. And that's a major improvement, especially when this is a very high degree of freedom problem, potentially hundreds of thousands of degrees of freedom. It's a huge advantage to be able to just work with one function, one scalar value function, if you know what to do with it. So we looked at Hamiltonian systems arising in mechanics. So I told you how Lagrangian mechanics, which originally starts from Newtonian mechanics, then turns into Lagrangian mechanics using the Lagrangian kinetic minus potential, through the procedure called Legendre transformation, can be turned into Hamiltonian. This is the Legendre transformation. Let me skip the details, but there's a procedure to introduce Hamiltonian. This is the generalized momentum associated with the mechanics problem. You get it as a derivative of the Lagrangian with respect to velocities. You put that here, you multiply it by the velocity and subtract the Lagrangian. So this is the Hamiltonian. It leads to Hamiltonian equations of motion, right, in mechanics. Another area, and I gave you an example, the pendulum. This is what the Hamiltonian equations of motion look like for the pendulum. Another example is a very different area of mechanics. And mind you, although you could say that, well, it's not quite different because it's incompressible fluids, right? So fluid mechanics. But the Hamiltonian nature here comes in a way that's a bit different, right? Because this is not about positions and momenta as you would for mechanics, but it's only in the position space. So when you look at the motion of particles purely in terms of their positions, there's no momentum involved here, right? So it's not the same type of mechanical structure that we have discovered for classical mechanics problems that I described. it's in fact, it has not much to do with, say, conservation of energy. It has everything to do with conservation of volume, in particular in 2 dimensions, conservation of area. So conservation of area imposes a Hamiltonian structure. The conservation of area as mandated by the divergence-free nature or incompressible nature of a velocity field implies, I mean, went through the argument, that you have a Hamiltonian for this problem as well, and that Hamiltonian is the stream function. So in the mechanics setting, the Hamiltonian was important. It turned out to be important because it was the total energy, at least for holonomic systems. And in fluid mechanics, again, the Hamiltonian has a very important meaning. It's the stream function. So the Hamiltonian structure can be tied to the stream function. Okay. I also noted that if you have that was the third example, that if you have just a completely general planar autonomous system, potentially has nothing to do with mechanics or even physics in general, but you've written down a model for something, and you find that that model has a conserved quantity. So a first integral, as we say sometimes in dynamical systems using classical terms, it just means that it's conserved along trajectories. Then also, first, you can show that that system will have a generalized Hamiltonian structure, which means it almost looks like the classical Hamiltonian we looked at, except that before that JDU, U playing again, that conserved quantity being the Hamiltonian, in front of that, you have a factor, a scalar function that multiplies the structure. So this is this is one way to generalize Hamiltonian systems. But then I went on and showed that with the rescaling time, and this is rescaling of time is very important to keep in mind. In a lot of contexts, this really helps with the analysis. It can remove singularities from dynamical systems. And the idea is that whenever you have a dynamical system of any dimension, all right, like this one right now is 2-dimensional, but it can be any dimensional, and you find that there's a common factor multiplying all equations, it's the same scalar. And as long as that scalar is non-zero, and it bothers you because it's nonlinear or singular or something, you can rescale time and remove it from the equation. So in the new time, which is a trajectory-dependent rescaling of time, because I'm taking the scalar factor and I'm evaluating it along trajectories, which I don't know at this point. But the beauty of the thing is that I don't have to. So it will be assuming that I already know the solution, which I don't have to in the end, and plug it into P and integrate this. So I simply integrate the scalar factor along each and every trajectory. Now, if P is non-zero, okay, then it has the same sign always. So this integral will be either growing in the positive direction or the negative direction. So its value can be used as a new time because it's growing monotonically. That's the point, right? Strictly monotonically, in fact. And that has to do with the fact that P is non-zero and hence is a scalar. So as I integrate, it either grows or decreases, but that value can be used as a time, as an integrator. And sure, that's what I'm doing here. But in terms of the new time, when I introduce that as a new time and differentiate with respect to it, which I get to by simply writing x dot using the chain rule. That's first dx by d tau, the new time, and then d tau by dt. But d tau by dt is just p of xt. But then I forget what the time dependence was. I don't need to know it. I just write p of x. And the result of that, p of x appears both here and there, and I cross them out. Okay. So in this new rescaled time, this is a classic canonical Hamiltonian system. And mind you, I can perfectly analyze the orbit structure of this system. I can see stability properties. I can establish various properties without having to worry about how exactly that P was depending on x of t. If I were to translate the actual time dependence of trajectories to the original setting, then I would need to know this. But most often, that's not what we're doing. The most often is when you look at, say, planar models, low-dimensional models, mostly qualitative behavior that matters. And in terms of the orbits, this has the exact same orbits as the original one, which is this, right? It's only how time is ticking on them. That's the question. All right, so that's the point to which I got last time. Any questions? If not, there's an example that will actually lead to a homework problem. I only mention it here because, and I like to mention this because this does show the diversity of Hamiltonian systems. So this was whatever example 3 it's a sub-example, because right now in the set of examples of systems with first integrals, and this would be a homework problem. It's it's actually from a model from population dynamics due to Lotka and Volterra. I think it's from 1925, and the story goes like this: that there was an interesting observation around that time, a few years earlier, that fishermen who worked on the Adriatic Sea reported some periodic variations in fish populations, and people just didn't understand why. In one year you have a better catch, and then the other year worse, and then it shows a period, not necessarily 1 year, but it does show a period, and people were trying to understand why that is the case. It was not related to seasonality. There wasn't any sort of obvious driver that would explain that frequency, right? And then I think a mathematician, and perhaps one, I forgot which one was, I think Lotka was probably the closer to biology, because Volterra has things named after him in analysis. So they got together and they looked at this problem, and they basically wanted to look at the simplest possible model. The fish without the fish, without the fishermen, the fish still have sometimes a hard time if they are prey and there are predators around, right? So they felt that the minimal component that one needs to use, because, oh, by the way, the fish population was varying without, that was the perception, without any interference from the fishermen, right? Just by themselves, right? So then you need some sort of a two-component system, because if you just have one component, then we have actually seen the models, right? You either get exponential growth when you have unlimited resources for a population, which is unlikely in real life. But if you have resource-limited populations, then what do? I mean, we discussed this last time, pretty much when we were hoping that the number of new infections would saturate, or not the number of new infections, that the number of infected individuals would saturate at some point when the virus runs out of steam. So that's a resource-limited population growth type of example. But then again, that doesn't explain the periodicity. So you need something else. So this was the first such ideas, and it has been very influential in population dynamics ever since. So if you take HT to be the prey population, and then the new element was to add something at the predator population. Okay, then both of these only make sense if they are positive or zero. If one of them goes extinct, then your first inclination to model this is the following. Well, the prey by itself would grow exponentially, right? So it would satisfy a linear differential equation like this with some constant h, a1, okay? Now, if you look at the predator by itself, if there's nothing to eat, there's no contribution from the prey, then excluding any cannibalistic behavior on the part of the predators, they would actually go extinct, right? So that means that it's a similar procedure with some other A2, but it's actually, sorry, P, it's actually decaying exponentially. So you would have A1 and A2 as positive constants, right? If they don't know about each other. Now, luckily for the predator and unluckily for the prey, they know about each other. So let's worry about the prey first. So its growth will be certainly tempered by the number of predators around. And again, the simplest way to temper that growth would be to throw in some constant B times P. And the more you have from the predator population, the more significant this term becomes. Of course, you would have to tune the parameters, but when BP hits 1, actually you stop growing, but it can also become larger than 1, at which point the prey population starts decreasing, okay? And interestingly, something similar happens to the predator population, that their growth would be mitigated by the number of the prey, because the population of the prey, because the more prey you have, the less you will be, the slower you will be going extinct. And in fact, if you have enough prey, H is large enough, then it can turn the trend around and you start growing. Okay, but of course, then there's an interaction here, because if you then start growing, there's too many of you, then you will eat up the prey, and the prey will then really is going towards extinction, at which point you have nothing to eat because there's too many predators now and too little prey. So it starts impacting back the predator population, and the predator population then goes down, and then there's some encouragement after a while to the prey, and so on. So there's a dynamic interaction between the two. And that's what the model is all about. So you would also then require these to be positive. Okay. So this is a nonlinear system, and it has nothing to do with mechanics for sure. And it's based on first principles of population dynamics, which were probably non-existent at that point in time, but this was the model that probably established those first principles. Okay. If you do a numerical study of this model, of this nonlinear system, very easy. You would ask ODE45 or a solver to plot the types of orbits that you have. Then H and P are the ones that you would plot. And of course, you cannot go into the negative domain. Then the numerical results would show that you, in fact, get indications of closed orbits. That's what it seems like, several of them. Now, am I just lucky, or am I just hitting limit cycles, which are attracting solutions that I have launched? Or are all solutions periodic? Do I actually have perhaps an equilibrium in the middle, which is hard to see unless it's asymptotically stable, and it doesn't look like it's asymptotically stable as it seems from the simulations. Nevertheless, if you do careful simulations, this is what arises. So, which is very good news at the time, because it is capturing the phenomenon that people set out to explain. Look at the variation of H and P, it's periodic. And then you can ask, what the period depends on. It will depend on the various constants involved. But because of these dynamic interactions that I just described, the hand waving turns, the ODE knows that in response to that. So this is the first successful example of explaining an observed phenomenon using population dynamics. But the point I want to make out of this is, and this will be a homework problem, show that this is a Hamiltonian system. And the way to show that, because it doesn't fall in the canonical classes of problems that we have, for which we got a blanket statement that it's Hamiltonian. It's not a mechanics problem. It's not a two-dimensional incompressible fluid. So the only method you've learned so far is to show that it has a first integral. And then we have this general result that if you have a first integral for a planar system, that it is at least a generalized Hamiltonian system, possibly a canonical Hamiltonian system, if you're able to rescale. You're able to scale out that factor P that I had there. So the way to that is find the first integral. So that would conclude the general intro. There are numerous other examples. We'll probably get to some of them, but at least you've seen 3 different areas in which you get a Hamiltonian system. So where are the proposed benefits? The proposed benefits would be that you get general conclusions without doing some work now initially, getting the general conclusions, and then you just by inspection, you find something is Hamiltonian, you immediately know a lot about the system. So what are the goodies that we would be able to use? So this part is now about properties of Hamiltonian systems. And I start from the very general, and then I move towards the more specific ones. So the circle of systems I'm going to be looking at, most of the time it will be completely general. So X is two n-dimensional, and H is just I assume that it's a differentiable function. So I have no problem with that, and I just remind you that J is just 0 identity minus identity. Okay, and n is bigger than or equal to 0. Now I said most of the time I will look at this level of generality, but in the first one I will restrict it somewhat, and this is about it goes about the conservation of energy. Now, the Hamiltonian is not necessarily the energy, but it's just helpful to think about it that way, right? And so I would say of the Hamiltonian. Now this one, I have to assume something, but this will be the only one for which I have to assume something. And the assumption is that the partial of h with respect to t is 0. So in other words, h doesn't really depend on position explicitly. It still can be arbitrary dimensional, it can be an arbitrary function, okay? Then the conclusion is that h is constant along all trajectories. So it's a first integral. So this is for all t. It's preserved for all times. So in other words, i.e., the Hamiltonian is a first integral. So if you're able to establish a Hamiltonian structure for the system, that immediately it gives you a conservation law immediately, and you don't have to check it on an individual basis. Now, why is this the case? I mean, you may have seen this in the context of mechanics or in various other contexts. You certainly didn't see it in two-dimensional fluid mechanics in general for the stream function, because it's not true for the stream function, given that in the general two-dimensional context, for an autonomous, for a time-dependent velocity field, this is not satisfied. The stream function will depend on time, and hence the stream value of the stream function will not be conserved along trajectories. Okay, but if you are, say, in a mechanics context where there's no time dependence in the potential, there's no time dependent external force, then this is satisfied. Or for instance, if this is really true, then just from the Hamiltonian, whatever you find has to be the conserved quantity, as I claim. So let's see why this is true in general. It's true by simply substitution. You plug in the trajectories, you differentiate them with respect to time, right? So by the chain rule, you take dh of xt, and there's no explicit dependence on time. So I just need to dot this with x dot, right? X dot of t. Now, if I write this as an inner product, then this is dh. It depends on x of t, but now I suppress that in the notation. We know that where I'm evaluating dh, and then I take the dot product of that with x dot, but x dot is right here, so that's j dh, right? Now, so what I have is an inner product of two vectors, dh being one, dh being the other, but the other vector, this is, in fact, there's something in between j. So what you see here is a quadratic form, and the quadratic form has a specific coefficient matrix, which, however, is not the coefficient matrix that we normally see when we learn about quadratic forms. If you have taken a linear algebra class, or you did some studies in linear algebra, and you heard about quadratic forms, then also always the assumption is that the coefficient matrix is symmetric. And it took me a while in my undergraduate studies. You know, first linear algebra teacher never explained why. It was very theoretically minded. Everything was trivial. So was this, but I asked the question, why is it always symmetric? Why can't we assume general matrices? Well, as I think already mentioned in part one of this class, you can certainly assume general matrices, but only the symmetric part will matter, because the skew symmetric part will cancel out. When you write this out as a sum, the skew symmetric part in the coefficient matrix will generate terms of equal magnitude and opposite sign, so they cancel out. So surely enough, because you only have a skew symmetric part here and no symmetric part, this is identically 0. And the reason is that j is equal to minus j transpose, okay, which you see by inspection. So in fact, this is then true in general, and you see that the skew symmetry of j had a major role in this. All right, so what does this buy for you? This is good to know, but are there any implications in terms of the language of modern dynamical systems? In that language, we look for structures in the phase space, and this doesn't look like a structure in the phase space. It looks like an algebraic statement. But if you try to think about what that means, it means that you will be, and this is a geometric view on this, that you will be confined to level surfaces of this conserved quantity, right? Because the trajectory, when you write down level sets, any trajectory that starts on a level set has no way of leaving that level set, because that would mean that if it passes to another level set or a point that is off the level set, is that the value of the Hamiltonian has changed on that trajectory, which is not possible, right? So the implication is that trajectories are doomed in terms of their initial energy. So they're confined to energy level sets. Of the form, say E, and I might want to label this as H naught, okay? And this will be a set, is the set of points in R2n, such that when you evaluate the Hamiltonian on them, you get H naught. So this is the energy level set, or sometimes called the energy surface. In physics, they like to call that. But is that well justified? Is that really a surface? So in other words, when I draw something like this, right? So H equals E equals the Hamiltonian, not E. The Hamiltonian equals H of X equals H naught. This would be that set here. And the picture that goes with it is that here I have a trajectory, right? Which is, once it has started on this set, so H at X naught is H naught, then this is X of t, and if I probe it at any point, then H of xt is still H naught, okay? And it's a useful constraint to be aware of, but is this term actually justified? Because first I said set, which can be anything. It can be very bad. It can be a point. It can be disconnected. It can be a Cantor set. That's still a set. And surface suggests that you have something smoother, and you hope that it's smoother, because if you want to do analysis, restrict your attention to an invariant surface, then it doesn't hurt if it's actually smooth, because then you can do calculus on it. So first I say what this is. This is then an invariant set. That's what we have called. Okay, but is this a surface? Is it really smooth? So, and this whole thing is taking place in R2n. Okay, so assume that what did I assume? Assume that, yeah, I assumed something, but it didn't. I'll go a bit general. X naught is taken from this point, H naught. So I'm on this point here, okay, right here, that point. And I assume that that's not a fixed point. So assume that J dH X naught is non-zero, so not a fixed point of the Hamiltonian system. So I really do move from that point once I've started a trajectory from there, okay? Then I know two things. So one of the things I know, that if I write the conservation of energy in this form, H, and I write out all the coordinates now, x1, okay, x2n minus H naught is equal to 0 when I, now I'm in trouble because these are the upper indices. So, okay, so x naught, the coordinates of that are x1, 0, blah, blah, blah. Not the best notation, but hopefully you get the idea. So I moved the 0 I moved here because I already have lower indices here. Okay, so when I plug in that initial condition, then certainly I get the little H naught energy, because that's where I started from. Okay, so I know that for sure. And so this is then, so so X naught then solves the general equation for the energy surface. This is the equation that defines the energy surface. Okay, So x naught is a solution to that. That's one thing I know, right? The other thing I know is that x naught is not a fixed point. So this j dx is non-zero, but j is a non-singular matrix. It's Q-symmetric, but it's not non-singular. So the only, if this is non-zero, well, even if, well, actually what I'm saying makes no difference. So if this is non-zero, then the only way for this to be non-zero is that what I already feed into the j, and that's why what I said made no sense, because this is true whether or not j is singular. If you feed a vector to a linear operator, a finite dimensional linear operator, and the end is non-zero, end result is non-zero, then there's no way that the initial vector could have been zero. So it has to be non-zero, right? Because any linear operator maps the zero vector into zero. So the only way for it to be non-zero is that it's non-zero, so that dh is non-zero. So dh x naught is non-zero, which then implies that there exists some index, at least one index in this gradient, which is non-zero, right? So there will be at least one partial derivative with respect to xi of h that I take at x naught that is non-zero, okay? So on the one hand, I have a candidate equation that I'd like to solve. Now, why would I like to solve that? I'd like to solve that to get an idea locally near that point what the surface is like, what that set is like. I'd like to see if I can continue that, solving that equation. I already know one of the solutions of that equation. And I also know that since the gradient is non-zero, then there exists at least one coordinate such that the derivative of h at that point with respect to that coordinate is non-zero. Okay. Now, I think you heard me praise the implicit function theorem a few times in the first part of the course. This is yet another case in which the implicit function theorem is tremendously helpful, because this problem is, the implicit function theorem is set up to answer this question. And the implicit function theorem says, so by the implicit function theorem, I found the solution, okay, which is this point. I'm sorry, pointing in the wrong place. I found the solution, this point, to this equation, right? That's good. That's how the implicit function theorem starts, the statement. And then I also found that one of the solution components, one of these coordinates, has a non-zero derivative. With respect to that, the Hamiltonian has a non-zero derivative. Then the implicit function theorem says that that particular one, then I can locally express in solving this equation as a function of the rest. Okay, so that means there exists a local solution to, let's call this star, this equation here, star, in the form I take that the one that I know I can express, xi, and I will have its value at the known solution plus f some function, which depends on x1, x2, up to xi minus I, that's xi plus 1, up to x2n. And I also know that this function is, that's the second added guarantee from the implicit function theorem, that this is, f is C1 if h is C1. So if whatever smoothness at least for me here at C1 is enough, so this is where the other variables enter. That I only needed to check, I've been only talking about one derivative here that had to be non-zero. But for this to hold, the other derivatives must also exist. So h must be C1, which I've always assumed, because otherwise it would be hard to talk about this system. I can, C1 means one's continuously differentiable. And it's the reason why I want the derivative not just to exist but to be continuous as well, because I want reasonable solution properties for this equation. And at least, in fact, I would need that the derivative is Lipschitz to have local unique solutions. Anyway, So this is a great result from the implicit function theorem, because it tells you that locally, this surface that we've been looking at can be, once I know it's one of its points, then I can continue satisfying this energy constancy requirement. So locally, this set that I have just defined in completely general terms is a nice graph over the remaining 2n-1 variables. So there will be a way to view this surface locally as a graph. So what comes out of this is that where is it? So EH0 is locally a smooth 2n-1 dimensional graph over these variables, over, I'll just say the remaining two n-1 variables. And this is one particular case of what we will be calling later in more precise terms, a differentiable manifold, a smooth surface. This is one particular case in which it happens to be a graph over a particular subspace, a smooth graph over a particular subspace, a very large subspace in this high dimensional space. So in later terminology, AH0 is a differentiable manifold. And the term we use for these, this is already something I used in Linear Dynamics 1, we'll say of codimension 1, which means that it has one less dimension than the phase space. How do I know that? Well, the dimension of the surface is the roughly speaking at this point, is the number of parameters you need to parameterize the surface, the minimal number that you need for unique parameterization. And here, the minimal number is 2n-1 because I've left out the ith variable. So it's a 2n-1 dimensional surface or a codimension 1 surface, and you're confined to that. So this term energy surface is well justified. It is a surface. We have the right intuition, as long as you are looking at a neighborhood of a point in the surface that is not an equilibrium point. So any point that's not an equilibrium point, in the vicinity of that, the energy set that contains that point is a nice surface. We even know its dimensionality. It cannot be any different. This is the dimensionality. Okay, let's check it on our standard go-to example for everything. Luckily, the pendulum has also turned out to be a Hamiltonian system too, right? So I can keep using it as an example for everything, right? So remember the pendulum equation, I did that derivation. Recall that's a Hamiltonian system. I'm going to write it out again. And the phase portrait in the Hamiltonian phase space is very similar to what we've seen before, because remember we had phi for the pendulum, which was the coordinate here, the deviation from the vertical. And before we did Hamiltonian mechanics, the other variable would have been phi dot in the phase space, right? That we would use. And now this is slightly different, because if I scroll back to that point, I forgot, here was the pendulum. The other variable in the Hamiltonian context is the momentum. And the momentum is just a scaled version of phi dot. So the angular momentum is just ml squared phi dot, right? So when you pass to the Hamiltonian formulation, you can take the phase portrait of the pendulum that you already know from the elementary description when we used positions and velocities, which we needed to do because the pendulum equation is a second order equation, and we need the first order view on systems, then we need to introduce these two coordinates. So basically whatever we learned there remains relevant here. is just the vertical variable is scaled differently. And this is P. Okay, we had M here. Okay, and I remind you, we have an equilibrium point here for the pendulum. It's the lower equilibrium point. We spent a lot of time on that. These are not perfect in my rendering, but these are supposed to be ellipses. And then you have the other, the upwards equilibrium point, which is at pi minus pi. And that looks like this. There's a separatrix connecting these. In fact, we have seen before that these are the level curves of the energy. So in fact, each is described by an H equals constant relationship. So what you see in front of you when you draw the phase portrait of the pendulum, you can interpret that as one way of interpreting it, and that's the one we've been following, is that these are the trajectories. But yet another way of looking at it is that this is the level set structure of the Hamiltonian, right? Which is the total energy in this case. So what you see here is the level sets of age, and as promised, as concluded, they are all invariant sets, except that we don't think too much about that, because in this lower dimensional example, the level sets themselves are one-dimensional. So they coincide in some cases with the trajectories. In other cases, they are unions of the trajectories, but they're not much larger than the trajectories, right? So let's see the statement. So what the statement was here, the conclusion was here from the implicit function theorem, that whenever I'm away from equilibria, so whenever I'm not at an equilibrium point, then the energy set is indeed an energy surface. So locally, at least locally, it's a differentiable manifold. It's a nice surface. So let's start taking stock. Well, and it's of codimension 1, right? So that looks like the case indeed for any of these closed periodic orbits, because there's no equilibrium point here. So I do have a nice manifold structure, smooth surface. It's not globally a graph over anything. That's an important point here again. I use this example for that. I said that locally, you can always write this as a graph over one set of variables, but the circle is not globally a graph over one-dimensional Euclidean variable. So that's a general feature of manifolds, that they're not, they should be actually, as we'll see later, they should be. A manifold is something that's locally diffeomorphic to a Euclidean space, but not globally. That would be too restrictive. That's why the circle, anything that's diffeomorphic to a circle is still a manifold, even though globally it's not diffeomorphic to R1, but locally it is. And that's good enough for anything to be a manifold. Being a manifold is a local property. Okay, so this is fine. Now, what are the problematic cases? It's also fine here, right? Which incidentally, this energy surface, if I don't view phi as a periodic variable, then this is even globally diffeomorphic to R1, because it never closes up. How do I know it's globally diffeomorphic? It's right in front of me. It's a graph over this line, right? So there's a one-to-one differentiable correspondence between that line and that energy level, which repeats itself periodically. So it's even a nicer manifold, if you will. Trouble develops when you actually violate that assumption, and you are in an energy surface that contains an equilibrium point, a fixed point, like here. Okay, so then you see that this is a piece of that energy surface, and locally that looks nothing like R1. It's not a smooth differentiable manifold. It crosses itself, and you could say, yeah, I'm not bothered by that, because this part is still nice, that part is nice, and that part is nice. But that point doesn't have an open neighborhood within the manifold, which would be diffeomorphic to R1. So this is locally here not a manifold. And the other extreme, however, it's still, I mean, in the sense of whatever they are called algebraic varieties, this is still piecewise smooth, right? And you can actually say that, all right, at least piecewise the dimensionality is okay because it's 1. But then it's even there's a more degenerate example right here, which is which is another point where the condition is violated. But then this is not even a one-dimensional manifold, but rather this energy surface, you could say it's a manifold, but so this is not a manifold, all right? But it's one-dimensional in the appropriate sense. This is a manifold because a point is a zero-dimensional manifold, but it's zero-dimensional. So it's not a codimension one surface. So this is a degenerate energy set relative to that. So just say that this is a codimension 2 energy surface because of the fixed point. And the other thing was here. Let me use a different color for that. Say this one. So this is energy surface is not a manifold. And in both cases, this is also reassuring because this is the only points where the manifold conclusion goes wrong. And we know why, because that assumption that you had a fixed point is not satisfied, right? That you're away from a fixed point, excuse me, is not satisfied. Okay, so that sort of checks out. Are there any perhaps more challenging examples when I can, but this buys me something. So let's look at an example, which is a higher dimensional. I'm not going to work out all the details. Some of it is in the, let's just do a 2 degree of freedom nonlinear oscillator. So it's about 2 coupled oscillators that move, say, in the horizontal plane without friction. So one of them is here, like so, and the other one is here. Typical sort of mechanics setting that you see in your dynamics class. 3 springs, and this is M1, M2. And I'm going to introduce 2 coordinates that measures the distances. This will be Q1 and this will be Q2. Here comes the twist, that these are actually, this is the notation, these are nonlinear springs, all of them. In fact, they're completely general. So the spring potentials are not necessarily quadratic. You have V1, V2, V3. And I assume very little about them. I would just say I graph them here just to sort of convey what I'll assume about them. But I need the negative part as well. So I assume that the springs are unstretched when you have the argument of the potentials is not necessarily Q, but so I will just say these are, sorry, this will be X. This keeps jumping, that's unintended, sorry. This will be X, and this will be VI of X, okay? And the shape of the potentials will be such that, for instance, this is allowed. I just want them to have a minimum at the unstretched position. And other than that, there's no more assumption except that they will be spring-like potentials. So I want to say that their second derivatives are all over positive. So they are convex, right? And I want, for all of them, VI of X, VI at 0, which is the unstretched position, equals 0. And VI prime at 0 equals 0. So this is the classic case when the springs are unstretched, that the potential reaches a minimum. But I'm not saying at all that this is a quadratic potential. It can be completely general. It doesn't even have to be polynomial, and it can be asymmetric, a complete nonlinear system. And I therefore have specified very little about this system. Okay, so I will just say these are general spring potentials. Now, if you head towards the Hamiltonian formulation, well, first you need the Lagrangian. Unless you've done this many times and then many times, but I haven't. So in this class, so let me write it out. Lagrangian, we've seen, is the kinetic minus potential energy. And the kinetic is easy in this case. It's 1/2 times n1 q1 dot squared plus 1/2 m2 q2 dot squared, right? And then I have to subtract the potentials. The potentials are also easy. They are additive, as any potential would be in this situation. So you would have V1. The only thing that requires attention is the argument. What is the argument of the potential? Well, the first one is easy because as the way Q1, whatever Q1 is, that's precisely the amount by which the first string was stretched. Okay, so that's what you have here for that potential. For the second potential, what is the amount by which it gets stretched? Well, it's not quite Q1 or Q2, but it's the difference of the two, right? So it's Q2 minus Q1. And finally, V3 reacts to, because it gets actually compressed. So when Q2 grows, then instead of stretching the spring, it actually compresses the spring. So the right argument for this one is minus Q2. Okay, and that's pretty much that ends the challenging part. So the very quickly, just the generalized momentum or momenta, because there's two of them. So what are the generalized momenta? You have Pi is defined as always the partial of L with respect to Qi dot. And if you do that differentiation as usual, that's just the kinetic energy, the partial with respect to Qi dot. That's Mi times Qi dot. Remember, this was the condition under which the Legendre transform worked, that the Lagrangian had to be convex with respect to the velocities, which I skipped. At this point, even if it wasn't, then I would face a problem because I could not invert this relationship between Qi dot and Pi, but I can easily invert that. Qi dot is just Pi over Mi, so I'm okay. This is indeed doable. And then we go back and rewrite the Hamiltonian as dictated by the Legendre transformation. So the Hamiltonian is, now it's a function of the P's and Q's, if I want to write it out. Well, let's do it the easy way. We have already seen that for any conservative mechanical system, meaning there's no dissipation and energy is generally conserved, holonomic system, time-independent potentials, everything. In the end, there was a general conclusion that the Hamiltonian is in fact the total kinetic energy. So I don't have to go through the hoops of the log, and doing the generalized momentum. I don't have to do the Legendre transformation because we got the answer already. Remember, if you don't remember, where was the answer? It was here. That as long as this was a general result, that as long as the kinetic energy is a positively homogeneous function of order 2 in the velocities, which is the case for these kinetic energies, then the Hamiltonian is in fact, Hamiltonian is always the kinetic plus the potential energy. So I can directly cut to the chase in this case and write that this is just T plus V. So I'll say C earlier. Okay. But the trick is that I have to write these in terms of the new variables. So this will be 1/2 times the MIQI dot squared. I have to rewrite in terms of the momenta. So this will be Pi squared divided by Mi, P1, and the same for P2 squared divided by M2, and the potentials don't change. And now they come with a positive sign, right? So that's V of Q1, V1 of Q1, V2 of Q2 minus Q1, plus V3 of minus Q2. This is the Hamiltonian. And then if I wanted to, I could write out the equations of motion. So the equations of motion, which I'm not going to write out, is x dot equals j dhx. And I just indicate that this is Q and P, and it's part, it's in R4, Q is two-dimensional, P is two-dimensional, and hence J is also in R4. So it's a four-dimensional differential equation, nonlinear, and I haven't given you basically any detail because I gave very little information about this. Is supposed to be smooth, right? Although just want to make sure we understand each other there. So this is very general at this point. The potentials are general functions, not even necessarily polynomials. Okay. Now in the notes, so the question is, can I say something about this nonlinear system? Can I use already to some advantage the fact that this is Hamiltonian? H doesn't depend on time explicitly, so H is a first integral. So that means that trajectories are confined to level sets of H. What are the level sets of H? I wrote out a little bit the details of that in the notes, but I think I can rely on your intuition and save you from going through those, a bit of algebra. But just look at, these are the unstretched springs at this point, and there are these two masses, right? The question is, based on your intuition, would there be any other equilibrium point for this system? If I displace the mass in any direction, then I'm either pushing or pulling one of the springs, right? If I try to preserve any spring as unstretched, I can only do that at the expense of stretching or compressing the other springs. So if you try to do this game, then pretty soon physically, you will see that the only fixed point, only equilibrium point for the system is the unstretched position. In any other displaced position, there will be forces acting on the two masses, or at least on one of them. And whenever you have forces acting on at least on one of them, the system will move, right? So that I think is acceptable even without the details. So note the only fixed point is x equals 0, but also see the notes for detail. Well, just no, but actually just see. But I think this is even believable without that. Okay, so that means, just think about the consequences. The only equilibrium fixed point is here. That means wherever I am in the phase space, I'm automatically on a nice energy surface. Not only locally, but the whole energy surface will be nice. It will be a smooth manifold, a codimension 1 manifold, because I started with non-zero energy since I'm displaced from the equilibrium position. So and hence I'm moving, and because I'm moving, I already have potential energy, right? So I'm not on the zero, and all the I'm in a displaced position, and all the springs, or at least one of them, I'm somewhere here, so it has a positive potential. So my total energy is positive. So I'm no way on the same energy surface as the fixed point, because that's an isolated occurrence. So the conclusion is that all non-zero energy levels, energy surfaces, are codimension 1 invariant manifolds. So the phase space, the whole phase space is foliated by codimension 1 invariant manifolds. I attempt to draw the phase space, which is not that easy, because what's the dimensionality of the phase space? This is a 2-degree, what we call a 2-degree of freedom, as I've said already here, mechanical system. The equations of motion are therefore 4-dimensional, right? So the phase space is then altogether 4-dimensional. So say you would have, say, as x1 here, you have x2, and then say I plot x3, x4 there. And in this high dimensional, oh, it's 4 dimensions, it's already high, I can't draw 4 dimensions. Everything is confined to invariant sets that are 3-dimensional. I don't exactly know their shape, but each and every motion which is away from the origin, okay, is confined to these sets. Now, can I say a little bit more about them? Because this is already interesting, right? I mean, we never had anything like this for general dynamical systems, that we worked hard to find stable, unstable manifolds, standard manifolds. We were only able to find them maybe near equilibria if everything lined up correctly. And I kept saying, oh, it's a local result, we don't know, whatever. Here, immediately, without any work, you get for a system like this, about which you know very little, right? That the whole phase space except the origin is foliated by invariant manifolds, and any trajectory that you start will live on that invariant manifold. Okay, so it would be then helpful to know what the topology of those invariant manifolds are, right? That because are they extended? Can they go to infinity? Are they bounded? What are they like, right? Because again, that's extra information so that you would be able to immediately make conclusions about the dynamics. So let's be a bit modest first, and let's try to just understand things near the equilibrium point, near the fixed point. Okay. So first of all, we know that so that's one conclusion here. And the other thing is that the fixed point is zero-dimensional again. Energy surface itself. And whereas these are two-dimensional, sorry, three-dimensional, codimension, one, three-dimensional. So what's our good old way of establishing, this is a nonlinear system. We first, let's not forget the rule, let's try to build up the phase portrait of phase space geometry gradually. How do you go about that? Well, first understand what happens near the fixed point. That sounds like a logical conclusion, except that I really don't know much about the system, right? Because I never specified the potentials. Let's see how far I get. So if I linearize, then what's the linear system look like? Well, if this is my linear variable y dot, then I just have to take the Jacobian of the right-hand side at the origin. The right-hand, here's the right-hand side. Where's my system? Here's my system. I take the Jacobian of this, I hit it with an additional differentiation. That means I can skip j, and I will have dh, the second derivative of h. So this is what the linearization of a Hamiltonian system looks like always, except that I need to take that at the origin, right? Sorry. Why? This is the linearized dynamics at the fixed point, okay? It's a 4x4 system, this matrix here. And I would need to do a stability analysis, I would need to find the eigenvalues of this. Now, the eigenvalues of this will crucially depend on the potentials, which I haven't specified, right? So it seems like I can't go too far, but from intuition, just imagining if these were linear springs, right, which we always get in mechanics classes, then we would know that this system would oscillate, right? So without doing any calculation, you can imagine that the eigenvalues of this linearization would be purely imaginary, describing oscillations. That's what we anticipate, but I cannot go into more detail because I don't know what the potentials are, A. B, in terms of stability, that's not a very good outcome anyway, because it's inconclusive in general. We learned that in linear dynamics 1, when you get purely imaginary eigenvalues, you generally have no idea what the actual true nonlinear stability is. Okay, so even if you gave me some information, given what we have learned before, that I wouldn't immediately have an answer in terms of the stability. Except that this is where, again, the Hamiltonian nature would help you. So the eigenvalues are unknown. But expected to be purely imaginary. So that means that linear stability analysis is inconclusive. However, we saw at least one tool that one can perhaps resort to in such a case, and that would be trying to find a Lyapunov function, right? That was our fix to this. But again, as I repeated many times, there's no magic trick for finding a Lyapunov function. You have to be lucky, you have to be insightful, and so on. Well, it turns out if you work with Hamiltonian systems, you're automatically lucky, because what is perhaps potentially a good choice for a Lyapunov function? Well, we only have one function in this story, and that's the Hamiltonian. Let's see if, even though we don't know the details of even the eigenvalues, or we don't know the details of the system, let's see if generally the Hamiltonian is a Lyapunov function that we could use to establish nonlinear stability. So the thing to recall about the Hamiltonian is that because it doesn't depend on time explicitly, it is a first integral. So dh dt along trajectories is 0, which actually implies, if I want to rewrite this, I will write something which is then clearly true, but trivially true. If something is 0, then it's certainly less than equal to 0, right? Good. And the other thing is that it starts looking like a Lyapunov function. Lyapunov's first theorem told us that if we find a function, remember, that is cup-shaped positive definite at the origin, and the derivative of the function along trajectories is negative semi-definite, then we automatically have Lyapunov stability guaranteed. So the negative semi-definite I already have. The question is, does it have the right shape? Okay. So what tells me the shape? Tells me about the shape of the function? Shape of the function locally is governed by the Hessian. I just need to take the Hessian of the scalar function. That's what we did for the Lyapunov functions, and see what the eigenvalues of that function are, right? In other words, which would be defining the curvature. So the second derivative of h at 0, because that's what I need to look at, is the following. Let's just clarify again what I'm calculating here. In canonical order, the variables are q and p. So I will have to take the Hessian with respect to this set of variables, okay? And the q dependence is in the potentials, and the p dependence is here in the kinetic energy, okay? So when I take the q derivatives, then I will be only hitting the potentials. And in the first part, is this the right? Right. So, but yeah, I did this in 2 steps. This has a structure of this. It's mixed structure, because when I take the q derivatives, then only the potentials will be affected, right? When I take the p derivatives, what do I want to say? No, when I take the mixed partials, there won't be any. And when I take the derivatives with respect to the p's, p1 and p2, then I see what they are fairly easily. They are 1 over m1, because this is a second order derivative, second derivatives, 1 over m2, or on m2, 0, 0. So this is the structure of the Hamiltonian. And this needs to be taken at 0, right? And again, the reason is that the d operation is the gradient operation. In this case, is the q partial and the p partial. These are vectors. So first I take the q partials, but that only affects differentiations with respect to the, only the potential depends on the q's, okay? And I take then 2 derivatives duly of the potential with respect to q. Here I would have the mixed partials for q and p, but nothing has a mixed dependence in this expression on q's and p's, right? So those partials will be 0. Likewise, these will be 0. And then I can evaluate the p partials twice. Again, that will only give me meaningful results when I apply non-zero results when I apply it to the kinetic energy. after the first application of the differentiation, the Q will cancel out. And when I then differentiate one more time, the P1, P2 disappear. So I will have 1 over M1 and M2. Okay, so what I'd like to establish that this is positive definite. And so this is positive definite whenever the upper left block is positive definite, right? Because this part is diagonal. I can only read off the 2 eigenvalues from here, okay? And also this Hessian then has an invariant subspace. And the invariant subspace would be the subspace of the Q1 and Q2 variables within which the partials are governed by this. So basically, it's this matrix that will decide whether or not the full matrix is positive definite. So it's positive definite whenever the Hessian of the potential is positive definite. So that leads me then to the calculation of V at the origin, okay? And remember what V was. I scroll back. This was the form of V. V1 depending on Q1, V2 depending on Q2 minus Q1, and then V3 depending on minus Q2. And remember that I assumed that they were convex, which means that their second derivatives, whatever I was plugging in, whatever location, that X might be just Q1, might be Q2 minus Q1 minus Q2, whatever, that is always a positive number. So when I take the derivatives with respect, this is 2 by 2, right? Because this is a Q derivative here. So it's 2 by 2. So when I differentiate the potential with respect to Q1, then the first one I will differentiate twice because that depends on Q1, right? So that will be double prime. Second one also depends on Q1, but whenever I hit it by the chain rule, I have to differentiate V2 with respect to its argument, but then because it's the Q1 dependence, I have to multiply by -1. But I do that twice, so the 2 -1s cancel out. So this then gives me V1 double prime plus V2 double prime. And I take the mixed partial, only this term depends on both. And when I do the mixed partial, both times I will do a prime with respect to the argument, but in one case I will have to multiply it by -1, in the other case I won't. So this gives me minus V2 double prime. Same here. And when I differentiate with respect twice with respect to Q2, then the Q2, I hit it twice with a prime, but Q2 is there with a positive sign, so that will not change my sign ultimately. I don't need to use the chain rule. And V3 depends on Q2 with this negative sign, but when I take second derivatives, then I will pull out that minus sign twice, so that will cancel out. So ultimately, this is V2 double prime plus V3 double prime. So if you look at this, you will find that V, and this is taken at Q equals 0. So V1 double prime at Q equals 0 plus V2 double prime at Q equals 0 is positive because I assumed that the potentials are convex, right? And the next thing that I want to point out, that if you then take the determinant of this full matrix, remember you then multiply this by that, and then you subtract V2 double prime because this becomes a plus. In that product, you will V2 double prime squared. In this product, you already have V2 double prime squared. So when you subtract it, you just have the rest of the products. But all of those products, the remaining products, V1 double prime plus V2 double prime, they are individually positive. So let me write that out. The determinant of d squared QV naught, which is based on sort of what do I get there? No, what I said was not right. What remains there is V1 double prime, V3 double prime plus V. So I'm multiplying these two. So it's V1, V3 plus V2, V3, because the V2 squared cancels out. And that's positive because all these terms are positive. So by Sylvester's theorem, or criterion, which would generally require, right, that all these leading minor determinants in increasing order until I hit the maximal determinant would have to be positive for the matrix to be positive definite, which I have here because this upper 1 by 1 determinant is positive and the full determinant is positive. So that means that this matrix is positive definite. As a result of that, remember the initial argument here. This is also positive definite, the Hessian of the Hamiltonian. Okay, so what do I have so far? I should probably actually number these. This was point number 1, and that resulted in this conclusion. And this was point number 2, which resulted in this conclusion. And for I can tell, that's precisely what I need for H to be a Lyapunov function, because I need H to be negative semi-definite, and I need to have it for it to have a local minimum at the origin. Okay, so when that's the case, then Lyapunov's first theorem if you don't remember this, then look it up in the notes. X equals 0 is Lyapunov stable. And remember, that means that it's non-linearly. So what does that mean? It's not asymptotically stable, but if you're willing to start close enough, you can force the solution to stay close enough. That's the idea of Lyapunov stability. Okay, and that's good. So that the Lyapunov stable. This calculation is now actually true for any dimensions. I have not particularly used. It was easier to do some of the algebra in 2 dimensions, but the conclusion is generally true that if you have a Lyapunov function, if you have a Hamiltonian, and the Hamiltonian and the system is autonomous, so the Hamiltonian always has this property, that's a first integral, and therefore has the property required by Lyapunov, and the Hamiltonian has a minimum at the origin, then automatically it's a Lyapunov function. So it doesn't matter in what dimension you are, you automatically have nonlinear stability for the origin. Again, this is very rare. When you have an autonomous Hamiltonian system, you automatically have a Lyapunov function in these situations. That's good. But my focus has been actually to try to understand the phase-space geometry. So have I made some progress towards that? Yes, I sort of get that the local solutions are oscillating, but I was hoping to get a bit more. I wanted to get a better understanding of what these level surfaces are. All right. So next step towards that is what I want to call the, so what are the local level sets, energy levels? What is the geometry? Of local energy surfaces? Okay. It can happen, and it does happen in some Hamiltonian systems, that even though you're oscillating and you're not leaving a vicinity of the origin with your trajectories, the energy surface is still unbounded. It just so happens that your trajectories do not cover the whole surface. Why should they? They don't have to. So the two are different notions. What is the geometry of the energy surface? Is it like a bowl or a torus or whatnot? And what the trajectories are doing. on it. So you could have oscillations, and yet you would not know what the energy surface is like, because it can just be an infinite carpet. Okay, so that's where I'm heading with this. That can we say a bit more? And the reason I'm doing that, because there's a very useful result from differential geometry that I want to recall here. And then, so this will be an aside. I'm doing proofs in this class when I feel that we learn something from the techniques, and this has more general applicability. So this is the result from differential geometry, and it's called the Morse lemma, which has been used a lot due to Morse, and he just called it a lemma because he needed it for something bigger. And it goes like this, that if you assume just you have a function f, which maps from Rn to, this is why, and this is an aside, we're stepping out from the Hamiltonian context. So it's a scalar valued function. It maps from Rn to R and is general, okay? And the f, the x is the argument of the function, okay? So assume that there's a point, I need to check my notation. So assume, yeah, x naught, assume that x naught is what we call a non-degenerate critical point. Point of f of x. A whole branch of differential geometry, differential topology deals with critical points of scalar valued functions. There are classifications. So what's a critical point? A non-degenerate critical point. First, what's a critical point? This is sort of old-fashioned terminology. The critical point bit is that when you take the derivative of the function df at x naught, then it vanishes. That's what it means for it to be a critical point. Basically, is x not in Rn? Yes, x naught is in Rn. The function is defined in Rn, so the x naught is in Rn. Thank you. So that's what a critical point, a non-degenerate critical point, is a critical point for which, if you take the Hessian there, then it's non-degenerate. So you look at the determinant of the Hessian of f at that point, and you find that it's non-zero. So you take the matrix of second derivatives of that scalar function, and you find that this symmetric matrix doesn't have zero eigenvalues. All eigenvalues are real because it's symmetric, but it has no zero eigenvalues. Okay. Then comes the statement that then near x naught, there exists a smooth change of coordinates, a diffeomorphism. You want that for change of coordinates. You want change of coordinates to be invertible, so you can go both ways, and you want it to be differentiable in both directions, so you can then operate. So these mappings will take smooth things that you discover in a better set of coordinates to smooth things without any funny distortion or introducing edges or anything. So that's a minimal requirement in general for changes of coordinates in analysis in Rn to be diffeomorphism. I mean, we've seen examples when we were working with funny spaces, right? The Cantor sets, then you only could get a homeomorphism because the space was bad already to begin with. But when you analyze shapes in Rn, then typically you want a good set of coordinates in which to study them. So you want your coordinate change to be smooth and invertible, and the inverse should be smooth. So there is a diffeomorphism which takes you from the x coordinates to the y coordinates, and I don't go into detail, such that in the y coordinates, if you rewrite your Hamiltonian, so basically, how do I do this? there was my original, my original Hamiltonian was h of x. Since I have a diffeomorphism, then I'm able to write x as a function of y. And I just didn't want to introduce a function for that. It could be h of y or something. I'm being a bit sloppy here. And so I'm now evaluating that function in the new coordinates. So I think of it as a function defined in the new coordinates, right? So the function defined in the new coordinates, once I have executed the coordinate change, will look like this. It's whatever it was at x naught plus the deviation from x naught. And I will have first a few terms, minus y1 squared, minus y2 squared, minus blah, 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 up to minus yk squared. And I tell you in a second what what k is. And then I have also pretty boring terms, yk plus 1, but all these will be featured with positive signs. Where k equals the number of negative eigenvalues of the Hessian. So what does this tell me? This tells me that this Hessian is non-degenerate, and since it's a symmetric matrix, it will therefore only have positive and negative eigenvalues, right? The Hessian, because of that condition. So separate the negative eigenvalues, if there's any, and then separate the positive from them. If there's k negative eigenvalues, okay, then the remaining, my chat disappeared, but I don't know where it is. Sorry, okay. The remaining eigenvalues are positive. And there is then a set of coordinates, a smooth, nice coordinate change, in fact, that puts your Hamiltonian, not Hamiltonian, that would be an application, your function in a particularly appealingly simple form. It's just what it was at the origin, or at the critical point, that is. And then you will have k of these coordinates squared with negative signs, and all the remaining coordinates in y will be added with positive signs, no coefficients, right? And also, there's no high order terms or anything. This is it. So in the appropriate coordinates, you will have an extremely simple polynomial representation for this function, not approximate, exact. And the polynomial will have two groups of variables, one group featured with negative signs, but all the same coefficients, and the next featured with positive signs, all the same coefficients, plus 1. And you will be able to say a priori how many negatives you will have. It's just intuitively simply exactly the number of negative eigenvalues that you can identify from the Hessian. Okay, so it's a very powerful result because it's true in any finite dimensions too. Okay, and you always have such coordinates. And conceptually, it's simple because then apply the Morse lemma. How much time do I have? 2 minutes. To the above Hamiltonian. So in this case, the Hamiltonian that I had here, remember, the Hessian was positive definite. So in this case, in this context, I have k equals 0 because the number of negative eigenvalues is 0. So the Morse lemma tells me, since I have a critical point for the Hamiltonian, we have established that, and it's non-degenerate, right? I'm checking all the conditions because the Hamiltonian has a 0 derivative and its Hessian is non-degenerate that we have seen, then locally, H takes the form in appropriate coordinates. So H can be transformed to this form, H tilde y equals no negative terms. And then so I just have y1 squared plus y2 squared plus y3 squared plus y4 squared. So that means that, and period, that's it. And that means that I can actually compute the energy surface is defined by this relationship in this, it's the rescaled energy or recoordinatized energy. So what is this? This is the equation of a sphere in R4, right? So what I end up getting is that in these new sets of coordinates, each local energy surface is exactly a sphere, S3. And it's embedded in R4, right? Is the true energy surface in the original coordinates an exact sphere? No, it isn't, but it's a diffeomorphic image of a sphere, because when I go back from the y variables to the x variables, that means, that's why I emphasize it's a diffeomorphism. All I'm doing is a smooth deformation of a sphere. So all local energy surfaces of h of x, now in the original one, are diffeomorphic to S3. So at least locally, I know what's going on. I've known that all energy levels are nice manifolds away from the origin, but I know a little bit more now, that they are, in fact, all of them are spheres, hyperspheres, sometimes we say. So this is my local energy surface. All my trajectories near the origin are confined to sets that are diffeomorphic to three-dimensional spheres. I will not stop there. Next time, we'll actually, now let's try to see if we can expand this knowledge. Is this really true then globally or not? And then we will have another tool, which is very useful from differential geometry, that will enable us to answer this question. Questions, if any? Okay, are we done today? Okay, no questions. Your last chance. If not, then I'll see you tomorrow. I'll continue from here. Have a good evening.